All right, today we're going to learn about something called related rates. We're going to learn to find a related rate, and we're going to use the related rates to solve word problems. So this is the application problems. What's really important about this is that in order to solve related rates, you're going to need to use implicit differentiation, because you're going to compare a rate of change that you know with the rate of change that you are trying to find. And these changes, these rate of change, is change done over time. So our independent variable is time. So t is now an independent variable. So any other variable would be our dependent variable. So to do this, first step you're going to do is identify the variable whose rate of change you are trying to figure out or trying to seek, and the variable for the rate of change you are trying to find. So I usually just say the rate of change I'm seeking, the rate of change I know. And then I'm going to draw a picture of the situation from the word problem to make sure I really understand what's going on, labeling the pictures with variables or numbers on there. Then we're going to distinguish constant quantities from variable quantities that change over time. So the difference in that, sometimes you'll be given some numbers in the problem. You got to figure out which numbers to use. Just remember that only the constant quantities, the ones that are constant throughout the entire problem, doesn't change as time passes, can be substituted into the equation at the beginning. Any variable numbers that occur at a certain time, you cannot substitute in until after you differentiate. Now that I identify that information, next thing I'm going to do is I'm going to write an equation. And this equation is going to be relating the variable of the variable identified in part 1 of the variables whose rate of change I am seeking with the variable of the rate of change that I know. So whichever variables those are, I'm going to write an equation involving those two variables. Then, once I get that equation, I'm going to differentiate everything, or sides of the equation. I will need to use implicit differentiation because I'll have other variables besides t, time. And remember, our independent variables, dy dt, dx dt. Then once I have differentiated, at this point, this is where I can substitute in some of those numbers that I had earlier in the problem. So for inequalities that depend on time, any of those variable quantities identified in step 2, I can plug that in now. But remember, do not plug those values in until after you differentiate. The reason that's so important is you're only looking at a picture, and if you differentiate with those variables as constants, you'll get a derivative of a constant 0, and you don't get the full picture. So make sure you only, those variable values, you only plug in at the end, after the derivative. Very last step is you have an answer, but you got to tell me what it means in terms of the situation that I have. So you got to interpret the solution. What that means is you're going to write a sentence for me, and you're going to write a sentence and make sure you answer the question. And please remember, you have to include units of measurement in this sentence. So your answer is always going to be in sentence form with units of measurements included. Okay, so that's the 6-step process for related rates problems. So let's just try a few. So here we have a hot air balloon rising straight up at a level field and is tracking by a rangefinder 500 feet from the liftoff point. So here is my balloon, pretty picture I know, and it's going straight up. So that's the reason I drew that line. And then off to the side, 500 feet from the liftoff point there is my rangefinder. So I'm just going to label some information on my diagram here. The next part says, at the moment the rangefinder elevation angle is pi over 4. Okay, so at the moment tells me that that angle changes as time changes. So pi over 4 is not a number I can plug in yet. It is a variable value, not a constant value. So I can't label this increasing angle as pi over 4 as you would like to do here. I have to label it by some variable. I'm going to choose my variable to be theta, because that angle, as the balloon gets higher and higher, that angle will increase as well. So there's kind of my picture of what's going on. So what we need to now is figuring out what rate of change are we seeking. So we ask, how fast is a balloon rising at the moment? So rate in which the balloon is, as height is increasing, is the rate of change we're going to do. So we'll describe rate of change as dy over dx or something like that. So I'm going to let my height of the balloon to be h. So that's going to be dh over dt. The rate I know is the angle is increasing at a rate of 0.4 radians. So that's d theta dt, since I named my angle theta. But again, so I need to come up with an equation so we're on to step, I didn't officially, I said some things about step 2, but let's distinguish our constant quantities and our variable quantities that change over time. So looking at a problem, we got a 500 is a number that was given to us. Pi over 4 is a number that's given to us, and 0.45 is a number that's given to us. So 500 feet, this is called a constant. I'm not moving that radar finder as time goes on. I put it down and it's staying there. So that's going to be a constant value. I can plug it in at the beginning. Now, the pi over 4 is a variable because as the balloon rises, as time passes, the angle gets larger and larger. And my hint was at the moment the rangefinder's elevation angle is this. So it tells me that that angle changes. So that's going to be a variable. I can't plug in pi over 4 at the beginning. I have to wait till after I take the derivative. So now I got to figure out step 3. I need to find an equation that relates h and theta, because the h is dh dt. So the variable of the rate of change I'm seeking is h, and the variable of the rate change I know is theta. So I just know from my trig class that tangent of theta is equal to h over 500. So I'll just use that equation. I've related it together. So I'm going to rewrite that h over 500 as 1 over 500 times h. That's not necessary, but that's going to help me take the derivative. So the derivative of tangent of theta is secant squared theta times d theta dt, because that's not the variable t. And the derivative of h, 1/500th h, is 1/500th dh dt. Now that I've found the derivative, this is where I can start substituting in the values I know. So let's see. I know that theta is pi over 4. So I can replace every theta with pi over 4. I also know that d theta dt, the rate of change, is 0.14. And dh dt is my variable, and that's the rate of change I'm trying to seek. At this point, what you're trying to seek should be the only variable left in your equation, unless you plug in your variable values. And so now I'm just solving this equation for dh dt. I'm going to multiply each side by 500, and that's 500 times 0.14 times secant squared of pi over 4 dh dt. And then I remember from my unit circle that secant of pi over 4 is the square root of 2, and the square root of 2 squared is 2. So 2 times 500 is 1,000. 1,000 times 0.14 is 140. So dh dt is equal to 140. Now I got to interpret what that means. Well, first let's find our units of measurement. The dh dt actually gives you your units of measurement. We have h variable on top. So what is the h variable what's the unit measurement for h? Well, that's the distance the balloon is high, so that distance there is in feet, because notice the distance I'm from the rangefinder is in feet, so my unit measurement is for distance is feet in this problem. And then dt is our time. Well, what's our measurement of time for our rates of change here was in minutes. So so the balloon is rising at a rate of 140 feet per minute. And that would be your answer. So you write a sentence. Oh, yeah, at the moment of interest. So sometimes you write at the time of interest, or at that moment the balloon is rising at a rate of 140 feet per minute, because as time passes the rate will also change. So pause and try this one. Okay, let's start by drawing a picture. Okay, so a 5-foot ladder is leaning against a wall. So here's my beautiful wall, and I got a ladder that's leaning against it. And our ladder the top of the ladder is sliding down as the ladder slides across. So let's see, 5-foot ladder. Does the ladder's height change as time goes on? No. It's a 5-foot ladder, it's going to stay a 5-foot ladder. So that's a constant value. And then, so we'll call that our constant. And then how fast is the top of the ladder be moving down the wall when the base is 4 feet from the wall? So when the base is 4 feet from the wall, the 4 is a variable value, because the hint was there when. We're looking at that. So the distance that the base of the ladder is from the wall is changing as time goes by. So I can't plug that in. So I can label the ladder 5 feet. But the other ones I got to have as variables. So the ladder sliding down and the bottom sliding out. And I'll just call this x and y. Just choose some variable for each of the sides. All right. So rate of change I know, and the rate of change I'm trying to find. How fast is the ladder moving down the wall? So that would be dy dt, and that's the rate of change I'm seeking. Now, what rate of change did I know? The base moves away from the wall at a rate of 5 feet, so that would be dx dt, because that's the base moving. Okay, so I need an equation that relates x and y together. I see Pythagorean theorem would be a decent equation for this. So I'm going to do my equation to be just x squared plus y squared equals 5 squared, because I needed something that relates x and y together. So I differentiate this equation with respect to time. Time is our independent variable. So differentiate both sides with respect to t. So derivative of x squared is 2x, but x is not my t variable, so I have to times that by dx dt, plus the derivative of 2y, y squared is 2y dy dt, and the derivative of 25 is 0. All right, now that I've taken the derivative, let's plug in every value that we can, because after the derivative, you substitute in your values. All right, so I know that I was given that dx dt is 2 feet. I was also given that when the base is 4 feet from the wall, so that's my x value. X on my diagram represents the base. And dx dt we know to be 2 plus 2y dy dt. Now I have a problem. Remember I said before, you have to have only, the only variable you should have left at this point is the variable of the rate of change you're seeking. And I'm seeking dy dx, but I have two variables, y and dy dx. When this occurs, what you do is you come up with a secondary equation. So you're just going to do an equation that's going to allow you now at this instant in time that we're looking at, we're frozen at, can we find y? And so I'm going to go back to my Pythagorean identity of x squared plus y squared equals 5 squared. And then I know at this instant in time, x is 4. And so I solve this equation. It's one of our Pythagorean triplets. And I end up that y is simply 3. So that means I can now go back to my original equation and replace the y with 3. And now I have only the dy dt, the variable, the rate of change I'm seeking, as my only variable. And that's what you need to make sure you have. And then I just solve this equation. So multiplying 2 times 4 times 2, that's 16, plus 6 dy dx, subtract 16 from each side, gives me 6 dy dx is equal to negative 16, divide by 6, dy dx is equal to negative 16/6, which I would simplify that fraction. Okay, so I found this. Now, the negative tells us that the rate of change is decreasing. Okay, that's what the negative on rate of changes means, that the rate of change is going down or decreasing. And so I'm going to use, when I write my sentence, I'm going to use the words for decreasing or going down, descending, whatever it makes sense in my problem, instead of the negative. I'm not going to put a negative sign with the number. I'm going to use it in my sentence. And that's illustrating this arrow here. So now that's where it comes, that's part of this interpret the solution in terms of your problem. So we're trying to find the rate in which the base of the ladder is sliding away from the wall. Oh, I just noticed I didn't put t, I put x here. It's so often, so used to doing dy dx. That should be our dy dt. So our y variable, you can figure out our unit of measure is in feet. Our t variable this time was in seconds. So my unit of measurement for this rate of change is feet per second. So the top of the ladder is moving down the wall. Down there gives my negative, at a rate of 8 8/3 feet per second. So notice I do not say at a rate of negative 8/3 feet per second, because the down is my negative, and putting two negatives there is like having a double negative in your sentence. It just does not make sense. So that's where the down gives us the negative value. Then we don't put it with a number. Please make sure you don't make that mistake. Okay, so now we're going to look at this example. Water running into a conical tank at a rate of 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? All right, so what I want to do first is I'm going to draw a picture to represent this. I'm going to draw a cone with a point facing down. And what do I know about this cone? Well, I know the radius of the cone is 5 feet and the height of the cone is 10 feet. And there's some water going in. So I'm going to put blue to make my pretty water in this tank. All right, so let's figure out which of these variables are constant and which are variable. So I'll pause and let you do that. 10 feet is a constant value, so I can label it on my diagram. 5 feet is also a constant. The height and the shape of this cone stays the same. It does not change over time. So those are my two constant values. And my variable quantity would be the depth of the water, because how much water is in the tank is changing as time goes on, so we're putting water into the tank. So the hint there was when it is 6 feet deep. So 6 is a variable value. So I'm going to let the radius of the water to be r and the height of the water to be h. So what would you identify as the rate of change that you are seeking? you should have got dH dt. Height of the water over time is the rate of change that we're seeking. What rate of change do you know? We know that water runs into the conical tank at a rate of 9 cubic feet per minute. So water going into the tank, what does that affect? That affects the volume of the tank. So dV dt, the rate in which the volume is changing, is the rate that we know, which is 9 cubic feet per minute. So now develop an equation that we'd use in this situation that involves the variable h and the variable v, so volume and height. Hopefully you figured out that it should be volume is equal to 1/3 pi r squared h. That's the volume of a cone. But we have a problem. This variable, this volume, this is the volume of a cone, and it involves the v variable and the h variable. But it also has an extra variable, r. And remember, we only need an equation that involves the variable of the rate which seek and the variable of the rate we know. The only way I can use this equation and find the derivatives is if I knew the r I could find r in terms of either h or v, or if I could find the rate of change of r. And so I think it's a little bit easier to find the variable r in terms of h. To do this, we have to remember something called similar triangles. So look back at the cone here, and I know if I, put a cross section of the cone that I have, the cone is itself has a height of 10 and a radius of 5. Now, if I did a cross section of the water, it has a height of h and a radius of r. These are similar triangles. And remember, the proportions of similar triangles is that I could say r is to h in the small triangle as 5 is to 10 in the large triangle. And I have a new equation. I could solve the secondary equation for r, and I could get that r is equal to 5h over 10, which simplifies down to h over 2. So I can go back to my volume equation and replace r with h over 2. You will always need to do this because you only need the variable of the equation that the rate of change you're seeking, and the variable of the rate of change you know. So doing a little simplifying this down, I end up the volume is equal to pi over 12 h cubed. And now I need to find the derivative of this. So I'll pause while you find the derivative of this equation implicitly. Okay, so volume is equal to pi over 12 h cubed. 12 is a constant. So derivative of v is dv dt. I got to do the power rule here. And so I'm going to take 3 times my constant, which is pi over 12, and decrease the power h by 1 times that by dh dt. So dv dt is equal to, and I simplify that, pi over 4 h squared dh dt. Now I've actually found the derivative. It's time to substitute in our variable quantities. So the rate of which we knew, the rate of our volume that is changing is in 9 cubic feet per minute. So that's dV dt. H was given to us when the water is 6 feet deep, so H is 6. And dH dt is what we need to find. So so everything worked out well. I don't have to do another equation. Solve this equation for dH dt. So 6 squared is 36. 36 divided by 4 is 9. So I get 9 is equal to 9 pi dH dt. Divide each side by 9 pi. I get dH dt is equal to 1 over pi. Let's check our units of measurement. H is being measured in feet. And time is being measured in minutes. So 1 over pi feet per minute. Interpret the result in a sentence. So let's see. At the moment in question, the water level is rising at a rate of 1 over pi feet per minute.